everyone, and welcome to the Radium-226 Roundtable hosted by the U.S. Department of Energy Office of Science Isotope R&D and Production Program. We appreciate your interest in this timely topic. The focus of this roundtable is on safe handling practices of Radium-226, the planning, facilities, equipment, and technical challenges associated with this material. My name is Julie Easel. I'm the technical advisor with the Isotope R&D and Production Program, and I will be moderating this event. Before we begin, I do have a few logistics to go over. This meeting is being recorded. The recording will be posted in the next couple of weeks on the National Isotope Development Center's website. There are closed captions available. Please click on the closed captions button to enable them. After all of the presentations, there will be a questions and answers session. Please use the Q&A box in Zoom to ask your questions. With that, I would like to turn it over to John Neuhoff, Program Manager for Isotope Reactor Facilities for the Isotope R&D and Production Program for the opening remarks.
All right, thank you, Julie, and welcome to everyone. And I appreciate everyone joining us for this Radium-226 Roundtable. I think it's an exciting topic, an important topic to discuss and provide some information. We've lined up an excellent series of presenters and presentations for you and hopefully have a good discussion. So as everyone knows, there's been a surge of interest in radiopharmaceuticals that target cancer at the cellular level. Specifically, the properties of alpha-emitting isotopes make them well suited for treatment of cancer. They deliver high target-specific radiation dose due to their short and well-defined track length for targeted alpha therapy. So there continues to be a lot of exciting developments in research, clinical trials, for example, with Actinium-225. So the DOE Isotope R&D and Production Program has worked for over a decade as a leader in the development of production techniques, separation chemistry for relevant alpha emitters, including Actinium-225. So we're here today to discuss Radium-226, which is a valuable but limited feedstock. It can be used for production of alpha-emitting radioisotopes used in targeted alpha therapy, primarily Actinium-225, Actinium-227, Thorium-228, which is the parent material for radium-lead generators, and even Thorium-229. So 2 points in my opening remarks before we get to the presentations I wanted to make sure to get across. Working with Radium-226 is hard. It needs awareness of its risks, hazards, careful planning for its safe handling. It takes appropriate facilities, equipment, experienced personnel, procedures, operational controls to work with safely. And you'll be hearing from the various presenters about these various aspects of how to work and safely handle Radium-226. So engineering, administrative, and personal protective equipment controls need to be tailored to the use of Radium-226. So that's the first point, is making sure to know it's hard and needs awareness of working with Radium-226. Second point, it's mostly obtained from legacy waste medical devices and is a limited resource. It's important to properly use Radium-226 and appropriately steward Radium-226 throughout its recovery, processing, and ensuring the ability to recycle it as much as possible. So those are the main 2 points I wanted to give in the opening remarks as we go through the presentations. Note the things that awareness of the risks and hazards of using it and the controls that are needed to safely work with it, and that it is a limited resource and that we need to steward properly for its recovery and recycling. So we've lined up a great group of presenters, experts from various institutions around the world with expertise in handling Radium-226. The goal of this Radium-226 roundtable is to share best practices, lessons learned, convey the work requires sober analysis, planning, and implementation of appropriate controls. So I'm looking forward to the presentations and the discussion that's generated from the presentations in this roundtable. And as Julie said, we welcome and appreciate your participation in this roundtable. So I'll turn it back to Julie.
Thank you, John. So just a couple of other points. We will be changing the order of the speakers today. We received word that Lucienne Pilet-Cousin will be unable to be with us today. So we will get permission from him to see if we can get his presentation and have it put up on our website. The other presentations, as we receive them, they too will be added to the National Isotope Development Center website. So the order today, we are going to start with Joel Tingy. He's a laboratory fellow from Pacific Northwest National Laboratory, and I will let Joel introduce himself.
Good morning, everyone. I'm Joel Tingy from Pacific Northwest National Laboratory, and represent a great team of those working with radium. Let me share my presentation. So is it up, showing in presentation mode?
I can see it.
Yes,
Okay.
you can go to the first slide.
You need to back up onto your introductory slide.
Yeah, it's not moving. There we go. All right. So we do have quite a team at Pacific Northwest National Laboratory. And so today I'm going to share some of the best practices that we have in our processing of some obsolete brachytherapy sources. And so, as you see, we have a large team. This presentation was prepared by multiple scientists at Pacific Northwest National Laboratory. So at PNNL, we have gram quantities of radium. Again, they're all in obsolete brachytherapy sources. Down in the bottom of the slide, you can see a number of the different forms that we have. And so one of our biggest challenges is to be able to handle each of these forms and to open them. In our process, we're doing batches in the hundreds of millicuries per batch. And again, we're looking at both what we call our normal materials, the needles and tubes, as well as the atypical sources that you see below in a number of different forms that we need to open. So part of our challenge is to minimize dose to our staff, as well as contamination in the facilities. So in our process, the process that we go through for recovery of the radium-226 from these multiple forms is to cut the source, then to dissolve the radium-226 from the breach sources. Then the radium is then purified and dispensed to meet the customer's requirements. The dispensed liquid is then dried to produce a dry powder in the vial, which is packaged and shipped to the customer. We do ICP OES analysis and gamma energy analysis to obtain and verify the specifications and to ensure that we have the purity that the customer needs. As you see down in the bottom of the slide, the first 4 steps, the cutting, dissolution, separation, and dispensing, is all done in a hot cell. We then move the material from the hot cell to a glove box. The reason that we move it to the glove box is to ensure that the package that we ship to the customer, the outside of that package, has no contamination on it. And so that is our method of minimizing contamination of that outer package. Now, some of the greatest challenges we have are in minimizing the dose to personnel. And what we see is that there is a high beta dose from the progeny. approximately 90% of that activity grows in within 13 days. That has multiple issues with it, including material degradation from both the alpha and beta that is present in those degradation products. We also have the challenge of the gaseous effluent of Radon-222. Now, at the Pacific Northwest National Laboratory, our facility, which is called the Radiochemical Processing Laboratory, in the slide you see it called the RPL, exists on the Hanford site. Because of its location and the height of our stack, and the amount of material that we're processing, no abatement is required. We're able to allow all of that Radon-222 to go up the stack and be an effluent. That may not be the case in many of the places where the work is being done. We also go through great efforts to minimize the contamination because it can contribute to the buildup of dose in the facility, as in the hot cell as well as in the facility ductwork. And we also strive to minimize the emissions. If the contamination occurs, then there's a continual emission of radon from our process. Now, as we look at the ingrowth of the progeny, we see in this slide you have three different Bateman plots of that ingrowth of the progeny. The first one shows all of the progeny from Radium-226. You see the blue line is the Radium-226, and then the other three in this plot, because on the left is because of the time scale here out to 20 days, you see that the radon, lead, and bismuth all lie on top of each other because of the scale. And again, you can see that about 90% of that activity occurs in the first 13 days. Now, if you look on the top slide on the right, you can then distinguish in this log plot that again, you first see the radon, then the lead-214 comes in a little bit later, and then the bismuth 214 feeds in, but in about 48 hours, they lie on top of one another. On the bottom, we've now separated out the progeny from Radium-222, and you see the lead-214 and the bismuth-214 growing in and leveling off in just a few hours. So as we look at that ingrowth of progeny, that makes it clear that we need to be aware of being timely in our processing, particularly from the time in which we've done our separations to the time of packaging, so that we can minimize dose to our personnel. So some of the practices that we go through for each of these three challenges that we've talked about. The first being the contamination control. It's important for us, as John had mentioned, that the Radium-226 is a source that we don't have large quantities of, and so we want to maximize the recovery of the Radium-226. So an important part of that process is to minimize the contamination and the loss from contamination of the Radium-226. And so we work very diligently with secondary contamination containment in order to, as we open the brachytherapy source, we collect any material that isn't collected in our primary system. We do the same during the separation and evaporation. We recover that each time through each batch, and then we clean that secondary containment and retain that, all to maximize the recovery of Radium-226. That also minimizes the contamination in the hot cell, and minimizes the gaseous emissions from Radon-222 during the periods when we're not processing. We also clean the equipment after each batch and are very careful in maintaining good housekeeping throughout the process. All of that helps us to maximize our recovery and minimize the contamination in the hot cell. Even though we don't need to abate radon 222 in our process, we do control and monitor the radon 222 emissions. Radon 222 permeates plastics and rubbers, including O-rings, seals, and bags. And so we've gone to different types of containers in order to minimize the emissions of radon 222 in the facilities. Our primary containment is a stainless steel swage lock container, and that is our airtight container for storage and for shipping. And again, I mentioned previously the timeliness, that it's important that we work as quickly as possible from the time of the evaporation to packaging in order to minimize the dose from the progeny. Currently, we're able to get the dose to our personnel during handling to less than 2 millirem per batch. And we also monitor the activity associated with the progeny from the radon gas. We monitor our roughing filters at our hot cell and glove box, and we monitor at the stack. And at this point, we have not seen any increased dose at those roughing filters. So the dose consideration in our storage is important. Both the alpha and beta dose from ingrowth can degrade our product containers. We've done a study to look at that, and we've done that at 38 days. So in the pictures that you see here, the picture on the top left is at 36 days. This is in a container with 38 millicuries, and we see minimal darkening of the glass and no problems with the cap or the container. But at 65 days, we do see a significant darkening of the borosilicate glass vial. But we have noticed that the cap and rubber liner show no visual signs of degradation at 65 days. We have gone to using a metal cap, and that is the preferred cap to use so that we minimize degradation of the container as it's stored. We also shield all of our digital electronics to protect against the radiation-induced degradation that occurs to digital electronics from the alpha and high beta dose. Our packaging system, so the product is a dry crystalline solid. We went through that evaporation process to obtain that dry crystalline solid. The borosilicate glass vial minimizes the contamination of the product from the materials of construction that might occur from stainless steel. And so, as I mentioned, for long-term storage, we use a metal cap that's preferred. We have looked at using a metal vial if there is a need for long-term storage instead of the metal cap and borosilicate vial. Again, our stainless steel swage lock container is the airtight container. No contamination has been observed on the outside of the container. I think a big part of that is moving from the hot cell where most of our contamination exists, carefully removing that vial and clean it, and then placing it in the glove box where we haven't been doing the processing, and contamination is not detectable. Now, the inside of that swage lock container is likely internally contaminated at receipt from that glass vial, and also from the release of radon gas from that glass vial. So we ship in a type A package, and we ship it as yellow 2 or yellow 3. Now, because of the ingrowth that we've shown you in our shipping documentation, we go through a modeling process to model what the dose will be at receipt, not at the time in which we ship it. And we use those activities that we get from that modeling, because the activity and dose at the edge of the package increases as we go, as it's being shipped to the customer. So again, I appreciate the opportunity to share with you some of the best practices that we have. We do have a large production team. They're listed here, and we're grateful for the support of the DOE Isotope program in being able to process and provide Radium-226 to the customers. Thank you.
So Joel, thank you very much. Greatly appreciate all that information and work that Pacific Northwest National Laboratory is doing. Our next speaker will be Dan Strassner, a distinguished R&D staff member from Oak Ridge National Laboratory.
Okay, thank you, Julie. Let me get my presentation up here. All right, do you see that in presentation mode? All right. Do we have a pointer? Yes. Okay. All right, so my name is Dan Strassner. I'm at Oak Ridge National Laboratory, and we're working with Radium-226. Here's just a quick overview of what we're doing and the team. So in 2016, Ornell started kind of a focused effort to recover Radium-226 from some of these legacy medical devices that Joel mentioned. This recovery and purification is performed in hot cells at Oak Ridge National Laboratory, and this material is used mainly for production of radioisotopes at HIFER. Thorium-228 and Actinium-227 are the main products that we're interested in there. The Ornell team that is responsible for these activities is large and diverse. And I apologize, I don't have names for all those who are on the call that should be recognized, but it's a group of hot cell technicians, radiochemists, QA staff that helps us make sure we deliver high quality products. Of course, analytical labs are very important to analyze both gamma for radiological and for mass spec. Radiological control technicians, facility maintenance, just to keep everything running smoothly in the hot cell facility, transportation, safety, other support staff such as welders, manipulator maintenance is a big one, metrology to keep our equipment calibrated. My role in this project is project manager. I originally trained as a nuclear physicist and was involved with the production of radioactive ion beams for most of my career at the Hollifield Radioactive Ion Beam Facility here at Oak Ridge. So here's just a landscape of Radium-226. This is from a paper that Susan Hogel published back a few years ago, and Radium-226 is shown here. And it is important for a number of producing a number of alpha emitters. You can irradiate this with neutrons, such as we do at HIFER, and through neutron capture and beta decay, make Actinium-227, Thorium-228, Thorium-229, which would then decay to Radium-225 and Actinium-225. So that's one way to do that Actinium-225 production. You can also irradiate with protons, either low energy or high energy, depending on what you want to produce. You can irradiate it with gamma rays and have photo-induced reactions to do a gamma and to produce Radium-225, which then goes to Actinium-225. So Radium-226 is a valuable feedstock for a number of alpha emitters in this region. Ornell is qualified for working with large amounts of Radium-226. We have the HIFER, which is a nice production facility. We also have infrastructure, hot cells, glove boxes, transportation systems, safety systems in place, radiochemistry experience. So we're well suited to work with this and to produce some of the important isotopes that you can get from radium. This is not directly related, but it's just an interesting slide I put in here about the high flux isotope reactor here at Oak Ridge. And there's a hydraulic tube. You can just kind of see the tube going in here that allows us to insert and extract targets mid-cycle, so we don't have to wait for the cycle to stop, or so we can just irradiate for a specified time. And in some cases, the optimized irradiation time is less than a full cycle. There, in this hydraulic tube, there are 9 positions, and you can see here that in the center line of the reactor, position 5, we're getting about 2 × 10⁻15 neutrons per second per square centimeter. So that at that high flux, that allows us to optimize production, get high specific activity while minimizing other radioisotopes that would contribute to our waste. So this is the hot cell facility we're working in. You see a picture here of the cell windows. In this facility, we have a bank of 4 hot cells. One of these is used for transloading material in and out of the cell bank. Then these hot cells are built in place, they're not modular. And the larger hot cells here are 8 feet by 8 feet by 13 feet tall. So that gives us plenty of room to work in the hot cells, and we have in-cell cranes that help us to move equipment around. And you'll see here in the next slide, we also have a hot cell glove box combination, because when we're producing some of these targets, it's good to have dexterity. And so when we're producing targets, we can move from the hot cell bank over to the glove box and then back into the hot cell. We'll just move on from there. So fabricating targets. So we make solid pellets for irradiation at HIFER. Of course, heat is generated in the target during irradiation, and it has to be removed efficiently to prevent melting of especially of the aluminum target body. Aluminum powder is added to the radium-226 to provide good thermal conductivity. Also, there are tight dimensional tolerances on the pellets. Let me move this out of the way. Okay. I'm sorry. The picture of everyone is getting in my way. Okay, there. So in this picture, you can see 2 of the technicians working in the glove box. There's a lead shield to reduce whole body dose, and there's a camera inside, and you can kind of see one of the pellets that has been produced in this process. And there are tight dimensional tolerances to ensure good contact between the pellet and the walls of the water-cooled target capsule. Also, before we weld that target capsule shut, we fill with helium to improve heat transfer. During this process, finger rings are used to monitor dose to the hands. And also we limit the amount of radium-226 per pellet to control personnel dose. And as Joel showed, the ingrowth of daughters contribute to an increase in dose, a significant increase in dose. So when we're working in the glove box, we actually do all of the work in a single shift. So we remove radium-226 from the hot cell, press the pellet, and then take it back into the hot cell before the end of the day. We monitor emissions from the hot cell bank. The hot cells, of course, are maintained at negative pressure with respect to the surrounding work areas. There are 2 ventilation systems in these hot cells, which exhaust through a bank of HEPA filters and into a monitored stack, which is shown here. The main hot cell exhaust is high volume and vents directly to the stack. However, we do have a hot off gas system, or HOG system, that is high flow rate, low volume. And that exhaust gas passes through a caustic scrubber before venting to the stack. And that allows us to, we use the HOG system when we're evaporating solutions, And so the emissions from that are go through the scrubber, which helps to first remove any particulates, but more importantly, it kind of slows down the radon, and so the emissions are reduced. What you can see here, just an example of some of the emission data so in this stack, we have a small loop that goes through an air filter or a paper filter, and then that filter is removed and analyzed, and you can see kind of the spikes. And this represents this orange line represents the observation of lead-214 from radium-226 decay. And so when we're working with solutions, we do see spikes, but then it comes back down. The red line, or the blue line here, I mean, is lead-212 from thorium-228 decay. We have a significant amount of thorium-228 after the targets are irradiated. And the radon half-life there is much shorter, and so it's a lot easier with some delay to reduce the emissions from that. However, if the thorium-228 is free to exhaust into the main hot cell, then we do see a significant amount of radon-220 being released into the stack. We have some in-cell controls that we use to reduce the emissions. This schematic here just shows a vial that's being heated. You can either heat it with a hot plate or with a heat lamp. There's a Venturi collector here, which then goes through a set of condensers, which then the exhaust goes through a couple of dry rite canisters and a activated charcoal before being released to the hog. And again, this goes to the caustic scrubber before actually going into the stack. The picture shows a heat lamp heating up a sample in a glass vial, and then there's what we call the J pipe, which is the collector for the emissions during the evaporation, which then exhausts to the hog system. Anytime we open the doors to the hot cell, radon is released. Access to the hot cells is possible through a large door in the back of the hot cell or through access ports at either end of the hot cell bank. And there's a conveyor that goes between hot cells so we can move equipment between hot cells and out to this access port. So anytime the access port is opened, we do see radon release. Full PPE is required for anyone working in this area, including the powered air purifying respirators, or the PAPR. We also have in this area around the hot cells continuous air monitors, and those are used to monitor the radon levels. And depending on the alarms if the alarms go off, there will be an evacuation, either a local evacuation or a facility evacuation, depending on which alarms go off and how many of the monitors are alarming. During radiological work, personal dosimeters are worn and are to monitor dose and dose rate, and there's audible alarms associated with those electronic devices, both for dose rate and total absorbed dose for the job. There's also annual whole body and lung counts that are for the staff. These are sodium iodide and high purity germanium detectors that to monitor potential uptake of radiological material. We generate a lot of waste in this process. This is just part of the reality of it. The volume of waste, of course, is much higher than the volume of product, but we generate low-level radioactive solids. We have mixed waste. We have liquid waste. No true waste is generated in this process. With that really helps in getting it dispositioned and helps in the cost. All of our liquid waste are sampled and analyzed before disposition. The Waste Services Group will take that analyzed data and develop a load list. Typically, liquid waste are packaged in a 55-gallon drum and then put into this type A overpack for shipment off-site. all of our solid wastes are characterized using a portable germanium detector. And both for the in-cell containers, the smaller buckets and cans for collecting solid waste in the cell, and then also once those have been packed and placed into some of these larger B25 boxes or into 55-gallon drums, then those are also characterized using this detector before the shipping paperwork is completed for shipment off-site. In some cases, we've had very high activity levels in our waste stream, and we have used a type B container to remove waste from the facility. With various controls and planning, we've been able to minimize this requirement, but occasionally we've had to use a type B container. So that's kind of it on as far as the safety issues. I do have a few slides now to show some of the devices we've been working with trying to extract radium-226, and these are very similar to what Joel and his team have been working with. So these devices are stored here at Ornell in welded special form capsules and shielded 55-gallon drums. And we then, when we're ready to work on some material, we bring that into the hot cell, unload the drum, and open the special form capsule in the hot cell. And inside that special form capsule, there are a number of devices. Over the years, a lot of these were last used, in the 70s. And so there's not a lot of documentation about what's in the special form capsule. So when we open it, there's always an adventure. In some cases, we see plaques. This is essentially a lead block that has a little cavity hollowed out and radium placed into that cavity and covered with a thin foil. And that was used kind of to treat skin cancers. Here is a glass ampule that we found. What we like to see, because we've developed a system to extract material from needles and tubes, what we like to see is a special form capsule that looks like this, where there's lots of needles and tubes. In this case, there are some additional canisters as well, but just some more pictures. This is needles that we found in the device in the special form capsules. You can see there's a little eye here on these needles, so they would tie a string to that. The needle would be inserted to the tumor for a specified time and then pulled back out using a string attached to this eye. Some of the radium-226 is encased in paraffin, what we call a dumbbell, but there's just all different shapes. So the way we approach this is we mechanically disassemble the devices and then chemically dissolve the radium from the fragments. And here's a layout of some of the devices that were in one of the special form capsules. You see plaques shown here, some larger tubes and cylinders, a number of tubes, and this is the size of tube that our current device is able to handle. A number of needles shown here, just essentially smaller diameter. And so once we process those needles and tubes, we end up with fragments. And the way hopefully the fragments are open and the radium can be chemically dissolved out of the fragments. In some cases, during the process of opening these needles and tubes, the ends are pinched off and we don't get all of the radium out, but we get most of the radium out in this process. We do have a second device that can take those fragments and grind them down into very fine powder, and then we're able to get the radium out, all of the radium out in that case. Yeah, just a statement here that these devices contain various amounts of radium-226, and so yeah. All right. The process to chemically purify the radium-226 is not trivial. There's not a lot of information specific to the device as to what filler material was used. There is a lot of information over the years what types of filler material has been used, but not for a specific device. So when we're dissolving we see a lot of different things, a lot of group 2 elements, calcium, barium, et cetera, some transition elements, transition metals here, which probably contributes to some of this green color. A lot of lead and bismuth, and then of course platinum and iridium from the devices, because most of these devices are made out of platinum iridium alloy, very inert alloy, which is good for medical use. And not only must the chemical process be robust enough to remove all of these contaminants, we also wanted to make sure that we reduce the volume of waste generated as much as possible. So that has been developed, took some effort to get that optimized. I think this is my last slide or next to it. So storing radium-226, Joel showed some nice background information on why you on the ingrowth and the dose and daughters and all. What I show here, typically our purified radium-226 is stored in a low molarity nitric acid solution in a borosilicate glass. What we did a while back is we took a sample from these solutions and did a mass scan. These are the top 12 elements that were observed in those mass scans. And you can see the blue lines show the immediately after purification, and then at 30 days, 60 days, and 90 days. So there is some ingrowth of certain elements from the glass. And then if we're going to store radium-226 for longer term, then we dispense the solution into either glass or a metal vial, typically zircaloy vials, and evaporate to dryness as a solid radium nitrate. And as Joe showed some pictures of radiolysis in glass, we really, for long-term storage, you need to go to a metal vial, and zircaloy is a good option for that. And so finally, just show a nice picture. The credits to Andrew Burgoyne here at Oak Ridge National Laboratory, 3 glass vials with 1 millicurie of radium-226 each, and just shows the nice picture showing the Cherenkov radiation in those vials. So with that, Julie, I am done. I'm going to stop sharing.
Dan, thank you very much for that presentation and overview of Oak Ridge National Laboratory's activities and facilities and capabilities. Next up in our roundtable discussion is Pat Causey, who's the Research and Development Technical Manager, and Richard DeCare, who is the Senior Vice President for Research and Development from BWXT Medical in Canada.
Okay, just switch over. Let me know if you can see this.
Sure can.
Okay. All right. Thank you, Julie. So my name is Pat Causey, and I am a researcher and technical manager at BWXT Medical. My training was under Mike Baird at Queen's University, where I worked in transition metal chemistry. I then had an opportunity to work with John Valiant at McMaster, which was tremendously educational. And prior to working with BWXT, I had the opportunity to start up the actinium program at our national lab. And over to you, Richard.
Hi there, I'm Richard DeCare. I think the titles got mixed up. I'm not a senior vice president. I'm just a regular health physicist. In any event, I spent 5 years at a hospital in Montreal in the early 1990s as an RSO before moving to Ottawa to work at Nordion, which was purchased by BWXT medical isotope section in 2018. And I'll pass it back over to Pat, and we'll be back and forth on this presentation.
Okay, thank you, Richard. Personally, I find the RSO activities pretty useful. I don't want to say more useful, but very useful. All right, so as Richard touched on, BWXT, we have a long, strong history in nuclear technology going back to the 1950s. And in the mid-2010s, we acquired what was then known as Nordion, or originated as Nordion, which itself was a spinoff from Atomic Energy of Canada and focused primarily on the production of Moly-99. And since then, we have become identified as BWXT Medical Limited. In terms of what we do, we are a major supplier of medical isotopes, and these take the form of APIs, drug substances, drug products, and additionally bulk radiochemicals. I just want to point out one highlight here is our actinium-225. As mentioned earlier, it can be derived by a number of technologies, and we have produced it via spallation on thorium metal targets. And we have provided material into clinical trials and are about to submit our DMF imminently. So that's who we are. What we are is an isotope producer. And as such, we are licensed by the Canadian Nuclear Safety Commission, and we are designated as a type 1B. And so over here in the blue box, it outlines the programs that we are required to have in place for maintenance of our license. And I've highlighted a few because those are directly impacted by the addition and inclusion of radium processing. And that includes operations, radiation protection, environmental protection, waste management, and packaging and transport. So I'll touch on a bit on those as we go through it. Our license allows us to possess, transfer, use, process, import and export, manage, and ultimately to store and dispose of nuclear materials. And specific to radium-226, we are allowed to have up to 10 curies on site. One thing that I do want to highlight here is that part of our requirements is that we have to have a decommissioning plan for our activities, and that includes a financial guarantee, something that can come into importance when we're looking at the long half-life associated with radium-226. So in addition to our license, I described some of the programs that we have, and included in that is our packaging and transportation. And currently we have approval for type A transport of radium-226. And we have submitted to the CNSC an amendment to qualify one of our package solutions for type B shipment. And the packages themselves include a number of layers to the complete solution. And very critical to that is the leak-proof insert that ensures that any radon contamination can be controlled. In addition, we have import and export requirements. They, in accordance to our license, and as such, when we bring materials in from anybody who is looking to have material processed, we have a process to do that. Similarly, when we go to ship material out. Okay. Critically, we have facilities that are available on site. And specifically, we have a number of facilities, hot cells, that have previously been used for the production of radioiodines and radioxenons. And those are shown here. These facilities include the nuclear ventilation that's required for extremely high quantities into the hundreds and thousands of curies of these radioisotopes. And so these cells, we are currently undergoing upgrading and commissioning activities to prepare them for our planned radium-226 harvesting work. All of this work is controlled by our existing safety and radiation protection programs. So in terms of the process, we provide both products and services. And in this case, we've developed a process for bringing material in from sealed sources where we will ultimately, where we ultimately will harvest, we will purify, and we will resubmit the materials back to potential customers. And sorry, we have done this as a proof of concept with a single sealed source category 2 that we had here on site. And we have been following our developmental documents known as RDocs. And I do want to reemphasize some of the points that were made earlier regarding the recognition that some of these materials, the documentation that comes with them, is not always great. There can be surprises as capsules are opened, and as such, we have to go through steps where we identify and prioritize which materials will be best served through what process. As I mentioned, we've done proof of concept harvesting. We had on site our very own source. I've shown it here. We only had the one, so unlike the earlier presentations where they had multiples, I've had to blow it up. But that is a 10 milligram needle that contains radium. And when we did this processing work, all of our work was controlled under the work permit program, and we performed it in our R&D lab. This is actually a picture of Richard. He is a very engaged RSO, as you can see here. And during our process, we had a lot of concern and trepidation related to the control of radon. And what we were able to demonstrate was that we were able to successfully control that radon so that there was no adverse contamination or uptake events. We also have a number of analytical methods that were used in support of that, both gamma spectroscopy and ICP-MS primarily, along with alpha spectroscopy. So one thing that I do want to highlight is that we were very successful in our ability to control the radon. We don't necessarily have the same types of facilities as others, and so being able to make sure that we were not having a long-lived daughter radon, being able to provide contamination outside of where we were meant to have it was very important. I also want to come back to, we used to do radioxenons, also a radioactive inert gas. And as such, we had some legacy technology that allowed us to locally trap the radon. And by performing the trapping on the radon, we interrupt the decay chain that was discussed earlier, presented here again. And because of that, we were able to minimize any exposure to operators, while we're also able to maximize recovery of material. So by employing a consistent unidirectional gas flow, the radon was able to be trapped. And as such, by interrupting that chain, those high energy daughters, the lead-214, bismuth-214 with short half-lives, they can decay away because there's no longer any radon there that is providing material. Similarly, the traps themselves, initially they had no field on them at all because that field comes about from those high energy daughters. So we were able to remove the trap, remove the radon, and for our own sanity check, we did confirm that the radiation fields on those traps were effectively the same as what we were seeing on the initial source material. And it allowed the people doing the work to handle the radium itself with due care, but less exposure to the radiation hazards. And so this is our simplistic chemical processing where we look to open the sources. I think Dan did a very nice job of describing some of the challenges that can be associated with that, making the radium material available for dissolution. Often these radium salts, they are not well defined and they are not very soluble. So we convert that into a soluble form of radium, undergo what is more traditionally recognized as the chromatography necessary to separate out and purify the material, followed by our analysis of that material, where we are then able to dispense based on specific requirement activity and mass amounts and dry this down for our intermediate storage. In doing this proof of concept work, we've developed our process flow for our traditional brachytherapy needles. And all of this documentation, these procedures are being vetted and approved. We've developed procedures for opening of the special form capsules, as well as the actual chemical processing itself. And then the analytical methods that we're using to correlate or to confirm the execution, they have been primarily borrowed from existing qualified methods that we had in our Actinium-225 program. And because of this, we've now generated preliminary material specifications that our process is able to meet. And with that, I will hand it off to Richard, who is going to describe some of the radiation safety and biodosimetry considerations when handling radium.
Yeah, so our presentation is more from the perspective of someone getting, a group getting into this type of work. So one of the first things I was interested in is, I think, Pat, we can, something going on with your screen there. Thanks. So a lot of people are regulated by ICRP 68, and that's the standard that we were using for dose conversion factors for inhalation, and hopefully ingestion is eliminated through your rest of your radiation safety program. But if you look at the values for Radium-226 for inhalation, there's just type M classification there, and it's 1.6 times 10 to the minus 5 for 1 micron sieverts per becquerel, and 1.2 10 to the minus 5 sieverts per becquerel, and it doesn't really give you a lot of information. So in the educating myself and what else was out there, and looking at bioassay programs and things like that, the newer standards of the ICRP, instead of just one document, there's a series of documents, number 130, 134, 137, 141, 151. And 137 contains a very detailed chapter on radium. Also in that same publication is radon and thorium. And it breaks down different forms. So Dan was talking about, and I should say that thank you very much for Dan and the folks at Oak Ridge for accommodating a visit for us from BWXT, so we could learn best safety practices from them and their experiences, and it's very interesting to hear Joel's experiences as well. But a lot of you will be like me. You're going to be asked, you want to work on this important area to do these targeted alpha therapies, which are very promising. So it's something I think we all agree is necessary to do. You may be getting, as Dan was saying, the nitrate form. And the nitrate form is type F, which is not included in ICRP 68. And the dose conversion factors for inhalation are much more favorable. So these standards actually go and publish just some radioisotopes, but not all in their documentation. But they have, can you go page down, please, Pat? They have software, very detailed software, where you can choose the element and what isotope. You can choose the inhalation size. There's a wide variety of particle size you could use. In the absence of knowing, the default is usually to pick 5 micron. And you can choose with this software how you'd like the information presented, and it will actually show you for your standard reference man or person, I should say, a 24-hour urine sample, how many becquerels equals a millisievert, for example. You could look at it that way. You can see that urine here is maybe not the best thing to follow. It's the it's the urine colored line. And the top line is whole body count, or not whole body counting, but what's in the whole body. And then if we could go to the next page, please, Pat. They do have published in the document what you can find in the dose conversion factors with time going out for type F, type M, and type S. Type S is really uranium ore dust and coal fly ash, so it doesn't apply to us. Type F only lists the nitrate form. So of course, if you're processing it, you're going to see more forms than the nitrate form. So to follow the regulations, any other form, type M, for instance, is the one you'll have to use. Pat and I are curious if anyone has experience or seen anything with bioassay with the chloride version, with chloride compound of radium, because we would suspect that it would be more behaving like the nitrate version. So just throwing that out there if anyone has any information. Otherwise, we'll go to the next slide.
Hey, Pat, could you click on the hide of that Zoom.co is sharing your screen?
Oh,
Thank you.
So in the ICRP 137 publication, they list detection levels for a variety of bioassays. And you can see those listed here. And then our experience is there's commercial offerings that have 10 millibecquerels per liter of urinalysis detection limit that we have access to. And also right here in Ottawa, our national capital, we have the very good, well, excellent, really, human monitoring lab, which is part of Health Canada, Radiation Protection Bureau. And they have for a 1 hour lung count, they have a 60 becquerel limit for radium-226, which is better than what ICRP 137 is showing. And if you really wanted to punish someone and count them for 8 hours, we extrapolate that out, you could get as low as 20. But looking at what all these implications mean with that software on the next page, please, Pat. This is a bit of a busy slide, but we're looking at, on the left-hand side, the type F, and on top we have the urine sampling. And if we use those values that we have of 10 millibecquerels per liter, assuming someone accumulates a liter of urine, and you are working with the nitrate form only, and you are allowed to use by your regulator, ICRP 137, then 0.5 microsieverts is the implied dose detection limit from that sampling method. And at 90 days, the retention would still be 0.71. So that's excellent. So I've coded that as green. Type M, which is the default that you're supposed to use if it's not nitrate, which I think we'll mostly be have stuck with. The 24-hour urine collection is still not bad. It's 27 microsieverts at day 90, though if you did a 24-hour sample there, it would be 4 millisieverts. That's something you have to think about in a bioassay program. If you just do routine sampling and then you look backwards at it and you found something, what does it mean? If you're in the unfortunate position of having the type S, you would see that day 1 would only be 5.3 millisieverts at the 10 millibecquerel per liter measurement detection limit. And at day 90, it would be a whopping 909 millisieverts, which is 90 rem. Obviously not acceptable. Looking at the lower part of type F, under that graph on the left, if you did fecal sampling, the detection levels are quite good. 0.02 millibecquerels is what's listed in ICRP 137. We don't have a method to do that. And interestingly, when you read the literature, most of the sampling that's been done over time has tended to be urinalysis and lung counting, when fecal sampling seems to be the best way to go. So we're talking to people about potentially having them develop that, but existing, we just have urine. So type F for lung counting is actually not very good for a detection limit of 50 becquerels. So if we sampled someone for about an hour and a half, you'd be missing 18.5 millisieverts, or close to 2 rem. So that's not very good. So these are things you have to consider when setting up your program. And if we could go down to the next page, Pat. So we have our own air samplers that we've, continuous air monitors that we've purchased. We have ones that we've designed ourselves. And after visiting Oak Ridge, we've going the direction they're going and using the iCam from Mirion. Of course, it's a much older system. Mirion is the current owner of it, and they provided images that we could use in this presentation. So we'll thank Mirion very much for that. You'll see 2 in the top right, two iCams. The one on the right is has a moving filter, and the one on the left has a static filter. They have other options as well. One of the ones that we've purchased is got a separate sampling head, so we can move that around and have the electronics different and also shielded because there's a secondary detector in there, which can fool you if you're moving sources around in a facility like we often do. Our eventual plan is we have airline respirators is what we'll use with our PPE, not the powered type because we're already set up that way, so that's easy for us to do. And then just wanted to share an incident we had at Oak Ridge. They talked about the issues with containing waste and containing radium, and Joel talked about that in his presentation as well. It is an issue, and we made this mistake, so I wanted to share that with you. The small amount of contaminated waste, rags and such that we had from that fume hood experiment, we just put in bags that were taped and put those in a 55-gallon drum. We didn't create very much waste. It was a very small experiment. But later on, we added to it. And of course, what happened when we added it to a drum that already had waste in it, the radon had off-gassed from those bags. And the action of lowering the bag into the drum shot the radon out of the drum, and that landed on the person who was doing this work. So they got contaminated with the radon progeny, most notably lead and bismuth 214. Now, the weird thing about working with radium-226 is prior to working with radium-226, most of the contamination incidents we found on our staff or visitors leaving at the exit monitors on, say, a whole body contamination monitor, most people are contaminated with naturally occurring radon. And our facility, we do measure the radon levels, and they're actually quite low in our facility. They're in most rooms, they're around the 10 becquerel per cubic meter level, which is quite low. But we still are finding radon incidents from the progeny on people. And I'm sure everyone listening has this type of experience. So working with radium, normally if someone's contaminated at our site with radon daughters, we just say, well, that's nice, on your way. We don't really do anything about it because that's naturally occurring and our levels here are nothing to do with what we process. So this is a consideration for everybody is what are you finding in excess of what's normal? And a lot of work's been done on the ICAM. It has been traditionally used for transuranics, and they subtract out the natural radon that you find. So you have to play with the settings on that piece of equipment and maybe use negative alarm settings for subtraction. So that's what we wanted to share for things to watch out for. The person who was contaminated by that bag incident at the whole body contamination monitor was contaminated at levels that were less than other people who were getting natural radon progeny on them from just day-to-day work. So it wasn't very significant. And then what we could do is we took the person's clothing and isolated it for 4 hours and recounted it on a HPG MCA, and there was nothing. So it wasn't radium, it was the radon progeny. So that's things you can do to help your program. Over to Pat.
Okay, thank you, Richard. And then just conclusion of the slide, reiterating that BWXT Medical does have a long history and are adequately and appropriately set up to provide this service. We do have a wide range of critical capabilities that will enable this to happen. And with that, I'd just like to say thank you, and I will hand it back to Julie.
Excellent. Thank you both, Richard and Pat, for that, and also sharing lessons learned, an actual example. I think we learn a lot from those. Our next speaker is David Trump, Senior Vice President for Research and Development from Spectron RX.
Great, thank you, Julie. All right, so again, my name is David Trump. I am the Senior Vice President here at Spectron RX for Research and Development. And I've had the privilege of leading a very diverse team of people that work in chemistry, physics, isotope separation, radiation safety, engineering, and facility construction, on this project here, and been happy to be a part of this roundtable today, and also happy to share some of our experience in handling Radium-226 here at Spectron RX. A little bit about our company. It was started as a consulting company in 2004 for radiopharmaceuticals and isotope supply. But by 2016, it transitioned to a CDMO for radiopharmaceutical development, isotope production, and now we're up to about 150 people or so. Spectron X was founded by John Zahner and Anwar Rizvi, and several of us came together to support the effort of building the company into what it is today. And so now we have a number of facilities, including in Europe. We support 31 active projects that include production of a variety of isotopes and radiopharmaceuticals. We have experience with and use most of the isotopes that are common in radiopharm, and we are currently shipping these products all over the world. So our experience with the Radium-226, we're newer to Radium-226, and before we started down this road, we spent an extensive amount of time researching this unique isotope, and just spent many hours looking into how to handle it, the different safety aspects, and essentially what are we going to do with this isotope. And we essentially want Radium-226 because we use it as a starting material for Actinium-225 production. And so we use cyclotrons to accelerate protons. So we use the P2N reaction on Radium-226 to make actinium. And we're very familiar with accelerating protons. We have a number of employees who've installed and operated large numbers of cyclotrons. And this is very comfortable space for our knowledge base. So Actinium-225 is needed to support radiopharmaceutical production at our sites. We're short in supply and believe if we had more, we could really better support the radiopharmaceutical community. And radiopharmaceutical research with Actinium-225 is very active in our industry. And again, it's very, very short supply. So we want to be a part of increasing the world supply of Actinium-225. And I'll stop just for a second. We really appreciate the Department of Energy's efforts to put this meeting together, as well as supply Actinium-225. And for that matter, we also appreciate all the ongoing work by the different groups that are trying to increase the world's supply. And we definitely want to be a part of that effort. All right, so how are we using it? We are subjecting Radium-226 to low energy cyclotron irradiations. 16 to 18 MeV is a sweet spot, apparently for production of Actinium-225 using this P2N reaction. So the cross section here is we have this graph that shows this reaction. This is actual data from experiments I could find in the literature, and it's a pretty good agreement that this is a good 15 to 18 MeV is a good place to be. And we are currently loading very small quantities of radium-226 in our targets, and in efforts to gain confidence every day as we're producing actinium-225. So we have several cyclotrons, and we are going to be acquiring more. And so our goal is to do many irradiations of small quantities of radium-226 for longer times. We're not really looking to make large batches of actinium-225, which kind of comes with a variety of issues, and including loading larger quantities of radium-226 in these targets. But instead, we're looking at small, more manageable batches that are produced continuously. So here's kind of a concept of our process for actinium production. We have a loading cell here on the left. This is an early prototype version, and the targets that go in here, I guess I'll stop for a moment. The targets are kind of been our #1 priority on this project for safety reasons. We believe that it has the highest risk point on this project. It's obviously our highest safety concerns occurring with this target, how it's handled, loaded, and bombarded. And it's kind of been the biggest, I guess, overall commitment for our team. So the targets are loaded here and then sent to a CHS cell, capsule handling cell. And this particular unit is commercially available. You can see the manipulators holding a shuttle inside there with a target in the shuttle. Although they are commercially available, everything, there's nothing made for this process. And so we're finding that every step over the last year and a half, 2 years has been custom needs, things we have to invent, things we have to figure out how to test. So this shuttle that you see is a great example of that. The shuttle is then sent to the cyclotron, and what you see in the middle here is an IBA cyclotron with a beam line. So on the far left, you see a tube that comes down carrying the shuttle. It docks at the end of the beam line on the left, where it is irradiated for a certain length of time, a certain amount of microamps. And we have cyclotron operators that are monitoring many different parameters during these bombardments, which can go around the clock for days. And so they are that the training for these guys is paramount, and making sure that any little changes in any of the systems being monitored is documented and discussed, and make sure that everything is functioning normally. And then after irradiation, the target then sent actually back to the CHS cell, and target then transferred to the chemistry cell. The chemistry cell you see here against a early prototype. It's nothing in this process again is something that you can get off the shelf. So everything's custom built. We have a team of engineers and chemists, isotope separations folks that they've come together to take a considerable time to make these units. So inside this particular unit is the automated dissolution purification unit for the targets and radium actinium. So after purification here, the output is our actinium-225, as well as the radium-226, which, as we as I mentioned earlier, needs to be recycled, and great care needs to go into this part to make sure that we are wisely using this resource, which is limited. And so it's more important to us to get the radium back out efficiently and recycled than it is to produce as much actinium. And so a lot of care and effort and just research has gone into, how to do that and how to recycle that and then get it back to the loading cell for the next production. So I decided to put this slide in and at least list some of the safety concerns that we have, and they are extensive. There's, I could have done several pages. I picked, just some here that came off the top of my head in the first few minutes, but obviously the half-life of radium-226 is very long, and that's a concern to make sure it's contained. As they mentioned earlier, there's complexity with the progeny, one of them being radon, which is a gas, which is very difficult to contain. We have incoming radium that is mixed with beryllium, and of course we have neutron productions there, which makes it interesting for shielding and management there, as well as trying to separate radium from beryllium, and beryllium being toxic on its own. So there's a lot of complexities there. We have risk of irradiating then these new targets, how do you take a process that's not really known and design a target around that and give it specifications and do proper testing to be able to accept the design of the target for use. And again, we've been through many versions of targets to arrive at what we're currently using. A lot of technology in those targets. Safe irradiated target transfer, and how do we do that properly? Poorly defined chemical forms of radium-226 for incoming material. We do have some that are well defined, but there's many that are really poorly defined, and which can present a challenge for dissolution and extraction and things like that. Employee safety practices that have to be implemented, exhaust design, airflow cascades. How do you design this and model what's needed there, considering the risks? Preparing for contamination events. Of course, we work very hard to make sure that never happens, but what do you put in place, for this? You have waste handling, which is a whole different, process on its own. Storage of waste before it can be taken out. Charcoal filter management, facility cleanliness practices. How do you train people for this with methods and processes that we're inventing and designing equipment around? It's definitely a challenge. We have the long growing period, as mentioned, for the daughters of radium. So we, in terms of radiation safety and sampling testing, we have to account for that. Appropriate exhaust monitoring, quantitation of radium-226 and working isolators. There's that's a unique kind of challenge on its own in a radioactive environment. How do we determine this correctly? Workflow for transporting radium-226, impurities in radium-226 incoming material that we have to identify and understand and figure out, how that can go through this, because in the end we're producing, actinium-225, which has to be very clean material because it's obviously going in for drug production. And then finally, things that people tell us that some of their experience over time, unexpected contamination that crops up over time, and and then seeing some actual radium-226 for some folks that maybe is showing up on wipe testing in areas maybe where they weren't expecting. So all these things and many more things that we've spent countless hours going through to design every aspect of how this process can be managed safely. And I thought I would show this slide as well. It's a kind of conceptual depiction of our current actinium-225 production environment. So in the middle, we have our shielded isolators where these processes start. Those isolators are kept in sealed rooms. And those essentially that entire sealed room is in a limited access room, which is inside a limited access area. And that area is in a limited access area of the building. And so all of this is in, for us in an area of the building where we have from ground to roof sealed wall access there. So there's only a couple of places to get in this entire area of the building. And again, we have, of course, gowning and wipe testing requirements between these areas. We have separate exhaust, for the isolators and rooms. The exhaust starts with the point of use for the radium-226, where the snorkel is kind of like what was shown, in some diagrams here today, where we know that as soon as that radium, it has to be open. We have to open the vials. So the moment that that's opened, we know that there's radon gas coming out of there. Although, we again, emphasize the use of very small quantities of radium, probably not to the scale that probably some of the other people on this that's been presenting. Our operating hours are very tiny. So, but nonetheless, we know there's going to be some radon release there. So we have snorkels in place there as a first point of trapping of radon gas in the isolator. The isolators itself has charcoal trapping on the isolators and out. So it goes through 2 or 3 at least charcoal traps on its way out of that space. And then for us, we're trying to approach this as carefully as possible. So we have, again, all of these different limited access areas and sealed rooms, but to date we've done we've done extensive wipe testing in these areas. So we wipe test everything that's coming in and out of these isolators, and these things are very carefully handled in sealed bags, and bag and lead, some type of lead enclosure, and then sealed multiple times on its way out. But to date, we've not shown contamination on any of the wipes and that we've done. We use, an LSC, for this, and it's very sensitive. And then, so we've done well so far, and we believe essentially, if we can essentially contain the radium and focus on the radium, and then realize that the radon gas is going to have to be at least exposed into the isolator space. But with all this proper exhaust management that we've put in place, we've been successful so far, and feel good about it based on the fact that we haven't seen radon on its way out of the exhaust in the areas that we sample it outside of these spaces. So overall, we've been feeling pretty good about it, and again, intend to continue on, and maybe at the next roundtable discussion, we can give you updates on what we find as we continue down this road. Thank you.
Thank you, David. Greatly appreciate your time and giving us your perspective of the safety concerns with your operations. Our final speaker will actually be 2 speakers. Sven Vandenberg, who is the CEO from Pantera, and joining him will be Thomas Hughes from Belgo Process. So Sven?
Thank you, Julie. I hope you can hear me. The presentation I wanted to bring to you today is a little different because it comes from a different country than all of the others. This one is coming to you from Belgium, and it's because Belgium has a long historic experience and has quite some experience also with handling large quantities of radium-226 in hot cell facilities. And I'll hope to introduce you to some of that history here. So let me see if that wants to progress. Indeed. So just wanted to begin with the very start of the whole radium history, which is, of course, this very impressive lady, Madame Curie, and her discovery in 1898 of radium itself. I guess I don't have to dwell on this long, but I do have a special respect for the way that these people in those days were handling these materials. We think of them as somewhat cowboys, and they may have eventually had issues, but they didn't know what they were doing, and were trying to handle this already with some care at that point. Afterwards, when radium was used, it was handled with a little less care, especially when it was used as an ingredient in the luminescent paint. I guess everybody knows about those stories as well. But it was a very important application, and of course, the radium that was used in those applications is mostly lost to us. What is not lost, and you've seen already a couple of examples in the previous presentations, are the radiation sources that were used for, at that time already, cancer treatment. They were both external radiation sources for so-called Curie therapy, with more powerful rays than the X-rays. Sometimes even the daughter radon-222 was collected as an even more potent source of radiation. So hospitals would carry reserves of radium-226 just to extract the radium-222, which is then used as an external radiation source. But of course, also radium-226 was used as an internal radiation source for brachytherapy in the form of those needles that we've seen. I've seen a few photographs, and I can't imagine that must have been a very pleasant experience to get those needles inserted. But already in those days, there were treatments like that were quite successful. So what is Belgium's role in all of this? Well, at the time, of course, it was quite of a colonial area. And Belgium had a colony called Belgian Congo, where there were mines in the Shinkolobwe area, uranium mines. At the time, uranium, of course, not being a very interesting product, only used to color a few ceramics, and that was it. This is pre-fission era, of course. But what was interesting was the radium that could be mined from it. And that Shinkolobwe mine was a freak of nature mine with an enrichment of the ore of 80% in uranium, and therefore also highly enriched in radium as well. And that's where the factory in Olen in Belgium was extracting from that uranium ore from Belgian Congo, the radium. And there was quite some important quantities that were extracted there. This is a graph that you don't find very often, but you can see that in the beginning it was mainly the US trying to extract radium from the mines in Colorado, but soon after the discovery of that uranium mine in Belgian Congo, actually the entire radium trade was pretty much dominated by Belgium, also still at extremely high prices at the time. And only when a very similar enriched mine after 1935 in the Canadian Great Bear Lakes was discovered did Canada take over some of the role that Belgium was playing at the time. But more importantly, and more recently as well, and this is important for the timeline, a commercial project was started in Belgium which used over 200 grams of pure radium-226 for the production of actinium-227. Now, everybody's talking today about medical isotopes, and so will I, as you will see. But at the time that actinium-227 was produced, because we're talking about the late 60s, early 70s, so the middle of the space race, and also the idea of we need some form of power in space. And as there is plutonium-238 in the vehicles driving around on Mars today, at the time, actinium-227 was also considered a source of heat and power for space applications. So the project was to produce 20 grams of actinium-227 and the pellets that go with it in order to construct radioisotope thermoelectric generators. And of course, the radium itself came from the Union Minière, the Belgian company from its mines in Katanga. The SEKCN has today still, and had at the time already, the reactor BR2 in which this actinium-227 could be produced. And in Mannheim, the German company was going to produce the RTGs. So, as was said before, by irradiating radium-226 with neutrons, you produce radium-227, which then beta decays into actinium-227. If you irradiate it longer, you will produce the other isotopes that were mentioned by the Oak Ridge contribution. But in this case, the goal was to produce large quantities of actinium-227 and extract those from the irradiated targets. So those 200 grams of radium-226 were cycled through the reactor BR2 and then into a large, and these are the type of capsules that were used at the time, and then into a large hot cell facility at the SEKCN where the chemical extraction took place. And as you could see, there were several curies of actinium and thorium extracted from the capsules at the time. And you can also see that some of these capsules contain 25, 30, 35 grams of and curies therefore of radium-226. So these were very large amounts of this material, and I can only reinforce what was said before. Also in those days, a lot of effort had to be taken in order to work safely and in a controlled way with this material. It is not an easy material to work with, and the installations were quite large and required a lot of design effort. So a few photographs and a few historic documents from the scientific reports of SEKCN at the time show that this radium-actinium-thorium separation also went, of course, with the full radium recycling, which was also mentioned, and I can only reinforce it. There is limited quantities of this material available, so we should go through every effort to recycle it as much as possible. And of course, the welding of those capsules as well, in order to irradiate the material in the BR2 reactor. So a few photographs from inside the hot cells, and especially I draw your attention to those hot cells on the right. You will see them again later in this presentation. There were in total some 6 hot cells, one of which was multiple cubic meters in size, and had on the inside of the hot cell additional alpha boxes in order to process all of this material. Were hot cells specifically for the chemical separation, for the conditioning of the actinium, but also for the conditioning of the radium and the waste, all separated into different compartments. And then those hot cells 4, 5, and there was another hot cell 6 that you see on the right. Those were for the conditioning of the final product, the actinium, and also the thorium itself. At the time already, radon management, and of course with those large quantities, it was necessary also to limit the exhaust of the radon-222, was an important aspect of it. You see here part of the filtration system that was there, but the filters, the radon trapping unit had its own hot cell to sit in because of course it became highly activated or highly it accumulated quite high activities of radium-222. At the time, the radon trapping unit was still the classical charcoal traps, although they were in this case also cooled down, if I'm not mistaken. Today, as I will move into the application of this material more recently and for Pantera into the future, we have developed this method a lot further and are no longer in need to use the charcoal filters, we have more powerful radon trapping methods available. Here you can see the back side of that hot cell in which the filtration unit was installed. So a hot cell really only just to put the trapping unit in there. And it was a very important aspect, and actually one of the more risky parts of the whole operation, and one that they did have quite a number of issues with in those days. In 1974, they then decided to stop the production, and actually the actinium-227 that was produced was never used, unfortunately, for its purpose. It was stored and later on bought from the SEKCN by a small Norwegian company called Algeta, which was very shortly after that sold for a very large amount of money to Bayer. And that actinium-227, originally intended for power in space, became the very first source of radium-223 for Xofigo. The actinium-227, as I said, together with the thorium-228, and radium-226 were all stored at our BR1 facility. This is our graphite-based reactor here in SEKCN. In sealed capsules, you see some designs there, which are not too dissimilar of the designs that were shown earlier today. These were eventually also welded in. And so some 20, 30 of those capsules are still available today at the BR1. And the waste that was produced was stored at a facility across the street from SEKCN, which later became Belgo Process. And Belgo Process is also the place where Thomas Huis works today, trying to deal with this legacy of those days. And if it's possible, I'd like to give Thomas the word, and just tell me when you want me to move forward, Thomas, with the slides. Thomas, are you there? Maybe it's a little difficult. So Thomas, just interrupt me if you want me to, if you're able to unmute yourself. I'll just try to tell this part of the story. But as I said, it's not my piece of the work. Belgo Process is actually a company linked to the National Waste Processing or Waste Management authority, NIRAS, and it was founded after Eurochemique stopped its operations. Eurochemique was a pilot reprocessing plant in Belgium, which was later on became the basis of the La Hague reprocessing plant in France, which is still operational today. Eurochemique at the time was a European project with participation from the European Union and its member states, with about 400, 500 employees in this area next to the SEKCN, and it was a subsidiary at the time of ONDRAF. It is today a subsidiary of ONDRAF NIRAS, which is the National Waste Authority. So those 500 employees, they work for Belgo Process, and Eurochemique was dismantled as a first activity by Belgo Process. Their core activities are simply that: waste management and decommissioning. And it goes from hospital waste to the spent fuel of the reprocessed spent fuel and the spent fuel itself at nuclear power plants eventually, as they would move into an underground repository. One of the aspects of Belgo Process's operation is indeed the decommissioning of the Union Minière radium factory. Thomas, is that you?
Yes, can you hear me now?
Yes, there you are.
Okay. Sorry, there was something wrong with my Zoom settings. Yes. So thank you, Sven, to assist. So the rich radium history of Belgium also led to the production of a lot of radium contaminated waste. Today we still store a lot of radium waste from the decommissioning of the radium factory, from the actinium program from SEKCN. and also from the decommissioning of contaminated waste treatment facilities at Belga Process, where in the past SEK used these facilities to process the radium-contaminated waste streams. We have a lot of solid, low-level solid waste. Today we have around 4,000 drums in store, and also 300 to 400 shielded packages of intermediate level solid waste. You can see on the right picture of how these containers, these are big concrete containers of a few tons, were stored in the past. In the center, they have a cavity in which drums are.
Lost you again.
Yes, can
You're
you hear
back.
me? Okay,
Yeah,
sorry.
you're-
Okay. Yes, I'm using the web interface, so maybe this is causing some troubles. We also, in the intermediate level solid waste, this is mainly process waste that was generated during the actinium program. And these containers contain around 100 milligram up until 20 grams. The most active package contains 20 grams of radium. And we also have a lot of sources. They still come in every week. They are detected in scrapyards. So we have a lot of radium-contaminated waste in Belgium, and this can range from 10 milligram needles, and we also have some larger capsules with a lot of radium in stock. You can, okay. So for the low-level solid waste, this will start a big treatment campaign next year. So we will open all the old drums. We will sort everything, the burnable waste. We will send this to a shredding system, and we will package everything in PE EVOH bags. We did a lot of tests on the PE EVOH line bags to manage the radon emission. So this EVOA is used in the food industry, and it has a really low diffusion coefficient for radon. So if you use these type of plastics, you will not get any radon out for the low-level waste. So then the organic fraction we will send into our incinerator at around 1 to 2 tons per day. And there we can feed until 10 milligrams of radium per cubic meter. There we get a volume reduction factor between 50 and 100. Then the ash drums and also the inorganic fraction, metals and concrete will be super compacted, put inside a larger drum, and this drum will be welded. And then everything will move inside interim storage. On the photo, you can see one of our interim storage bunkers. And these bunkers typically contains 10,000 drums each. For the intermediate level solid waste, we will take these concrete containers, move this to our hot cell facility. We will pull the plug. Sometimes we need to drill the metal containment to get access to the waste. Then we will empty the containers, sort everything, dry the waste. Then we will move it in 80-liter drums, then compact it, put it in a 100-liter drum with a double lid system. This we will put in a larger container. We will cement it, and then we will also send it to our robotic welding station. Okay. There's some challenges I like to share how we deal with the radium waste because we already, I think, have around 40 years of experience dealing with radium. So for our PPEs, we send people inside the hot cells or areas where we have high radium contamination. We have some rules higher than 300 becquerel per cubic meter. We use full face mask, P3 filter, or active carbon, and a Tyvek suit. Around when we go over 3,000 becquerels per cubic meter, we use overpressure suit and a pressurized mask with the airline. And we also use nose swab and special body counting for the people that work in high radon environments. Because typically our body counting is aimed at detecting cesium and plutonium from our reprocessing past. And for the radon, there's a special type of body counting. It's also a little bit longer. For dosimetry, when we go inside the hot cell, our work on highly active packages. Because we deal with high dose rates, we need good work preparation, sometimes simulation for the high risk entries. It's always time and distance we try to focus on. For the monitoring, we use TLD for body dose, extremities, and also on the eye dose. And for the entries in the cells, we also use radio communication and teledosimetry to follow up what dose the people are getting. Radon management inside the rooms or cells, we use high renewal rates. Then we send everything to HEPA filters and send this to the stack. We do not use any radon extraction system. We have a high stack and we emit a lot of radon, but those impact to the population is considered to be negligible. Because we also handle a lot of transuranic waste, we like to have a large physical separation between buildings and operations of these materials. We also need to have a look at take care for the atmospheric conditions during discharge. If we open really large radium sources and we have no wind, then at the personnel monitoring systems, we have big queues. Next one. And the last point is the hydrogen buildup. When we open old waste packages, we had some incidents with this, especially when you have a lot of organic material inside. You can have a large hydrogen buildup. So what we do today for the packages, we use remote drilling, everything under ATEX, then venting, gas management before we proceed and get access to the containers. And also for new waste packages, we see, because for radon management, we like long-term storage, we use always metallic barriers. So we like to weld everything close. But if we have a lot of organic material or water inside the waste we see, we have pressure buildup over time, over a couple of years. So we need to go to regular venting or controlled discharge. Okay, this was my input. Thank you.
Thank you, Thomas. It was excellent. I hope I'm still unmuted. Yes. So you have now the history of Belgium, the way the legacy that created is being treated today by Belgo Process and the measures they have to take. Then we come to the future a little bit about the new applications. I've told you about Xofigo and the Actinium-227 that was at its origin. Of course, as you are radiating Radium-226, some of it also gets activated into Thorium-229, which was extracted by some researchers from the capsules that were stored at the BR1 and are used today as a very small generator for Actinium-225. We're talking here about less than 1 millicurie capability of delivering, which is also why it's a lot smaller than what US DOE and others are putting out on the market, but it's used for our own R&D. And it was a little bit at the origin of what today became Pantera, the joint venture between the SEKCN and IBA as a manufacturer of accelerators, aiming at the large-scale production of Actinium-225. Of course, Actinium-225, the alpha emitter that is very promising towards the use in medical applications. As you see here, the very famous first patient injected with actinium PSMA in 2014 in Germany, in the Heidelberg hospital. And of course, this promise creates a new demand for Actinium-225 and therefore a new renewed interest in Radium-226. So how do you produce it? Well, as was introduced already, you have to irradiate it, but this time not with neutrons, but either with protons for a direct production of Actinium-225. So your Radium-226 is directly converted into Actinium-225, or you can irradiate it with gammas for an indirect production production. With the gammas, you knock out the neutron from the core, produce radium-225, which then becomes a generator for several weeks of actinium-225. And in the meantime, you can irradiate other batches of radium-226 to produce your generators, and in that way have a continuous production process. So Pantera has chosen for the gamma route for several reasons. One of them being the fact that you don't have to deposit all of your heat in your target. We heard before from Spectron RX the challenges that creates. Also the challenge of having a failed target, of course, are significantly more risky if you deposit all of your heat in the target. So we have chosen to irradiate indirectly by using an electron beam, converting it into a high energy X-ray gamma beam if you want to. The advantage there is that we can enclose the radium in a sturdy double-walled container which is separately cooled, and therefore we have much less risk of losing the radium. The downside is that you need much higher quantities of radium, but as you could see from the previous slides, we do have quite a large stock of radium here in Belgium. So Pantera was created exactly for that purpose. Between SEK, who owns still today a large stock of pure radium-226 crystals, and IBA, which has the right accelerator for producing the electron beam, the high energy Rhodotron. And this is a small movie to help you understand how we want to approach this.
In the field of radiotheranostics, one of the most promising radioisotopes is the alpha-emitting actinium-225. But today, the lack of large-scale and high-quality production solutions is holding back its use for cancer treatment. IBA, the world leader in particle accelerators, and SEK-CEM, the renowned Belgian Nuclear Research Centre, joined forces and launched Pantera, a private company dedicated to setting up a state-of-the-art facility for the large-scale production of actinium-225. In that way, Pantera will enable the widespread use of actinium-based therapies against different forms of cancer. It all starts at the heart of the facility with the high-energy IBA Rhodotron, enabling the unmatched production of a high-power electron beam. This electron beam is converted into a gamma flux before irradiating a sealed radium target for several days. SEK-CEM currently owns a large high-quality radium-226 stock, securing operations for the many years to come. The gamma flux transforms the radium-226 into radium-225. The target is then transported to the radiochemistry labs, where it is safely opened thanks to a radon trap system installed on the hot cell. The radium-225 produced progressively decays, leading to actinium-225 buildup. Thanks to an efficient radiochemistry process, several extractions can take place, ensuring a high-purity actinium-225 recovery in a GMP environment. The purified actinium-225 is sent to the dispensing lab, where it is fractioned and sterilized. The radium-226 is recycled for a next production round, creating a sustainable process with low waste volumes. The actinium-225 is then ready to be shipped all around the world to be labeled before patient injection. Along with actinium supply, a drug master file will be available for reference to facilitate partner finished drug registration. By creating a widespread availability of this rare radioisotope and enabling access to innovating radiopharmaceuticals, Pantera brings new tools to medicine and new hope in the fight against cancer. New hope for a better fight for life.
There you go. To have a short view on our timeline, currently we're preparing the engineering of the facility and the completion of the drawings of the building. Actually, most of our technology is secured under a series of patents, and it will be a question of in 2025 starting the construction of our facility, which we hope to complete in 2026, end of 2026, early 2027, to install the Rhodotron and start the production in early 2028 and as a commercial supplier. Because you see this gap here in supply, and because of the need of earlier supply of actinium-225 for completing the clinical trials, Pantera also joined forces with TerraPower Isotopes to increase the availability of actinium-225. And in exchange for access to the technology that we propose, we have also been able to secure a generator based on thorium-229 that we will exploit. And this comes full circle for a nice facility, because those same hot cells that you see on the left and that you saw before, where the thorium radium actinium separation was done at the time of the actinium-227 project, are those same hot cells that will be used, of course, with a new interior and a new alpha box inside. But those same hot cells, those same shieldings will be used for the new housing the new generators. And we even brought together the generation of people that at the time in the actinium-227 project were part of the project, and some of the people that will be doing the extraction from the generator in the future. So this is what will happen. The thorium generators will be placed inside those hot cells. We have added to that a actinium final purification inside a GMP container lab, which is just outside of that building. And that will allow us to do the last step purification under GMP conditions and dispense GMP actinium-225 for use in clinical trials. And that, of course, fills that gap in our timeline. That production will start from the second half of this year onward, and we'll be happy to be part of this exciting adventure in nuclear medicine. Thank you for your attention, and if there are any questions, I think we're now ready for the questioning round, right, Julie?
That is correct. So Sven and Thomas, thank you very much for that presentation of what is happening in Belgium at this time. So Sven, there we go. So we have received several questions in the Q&A section, so I greatly appreciate it. Several of the questions are focusing around surface contamination in the hot cells, whether it's from the Radon-222 or its daughters. Such questions are as how much surface contamination, what was necessary to deal with that contamination, what controls that you have in place. Now, I know some of you touched a little bit on that, but if anybody would like to add any details on contamination or contamination control. Any of my presenters?
Julie, I'll just mention the hot cells are contaminated with alpha emitters. We process radium-226. We also process irradiated targets. So the contaminations are both the radium-226 and the produced isotopes. I do not have a good number, but I do know that personnel will not be accessing the hot cells. That contamination levels are high. A lot of it is from progeny of these alpha emitters, but there is some contamination. Now, we try to minimize that, because if you have a lot of thorium-228 contamination or radium-226 contamination, you'll have a lot of radon emission that is going directly to the stack, and we monitor that carefully. So we know that the contamination levels of radium-226, for example, are not extremely high. It's more the progeny due to radon emission.
So one aspect that BWXT is limited by, we don't have the very large facilities like the Oak Ridge labs have. And so because of that, we can't afford to have much in the way of contamination internally. And so we are going to be applying a very local control over each process step within the hot cell itself, so that we can reduce the, I would say, the availability of those contaminants inside the cell. making it easier when we have to remove materials from the cell.
I guess I'll just add, Pat, that with regards to the trapping of the radon progeny, in addition to what Pat's saying about contamination in the cell, we're looking at every step of the way in the chemistry of the process of capturing that into our traditional xenon traps, which have proved quite effective. The shape of our traps is like 4 cylinders connected in series, and the very first testing we did, there was a slide Pat showed about the ingrowth of radon. So we took that off, and we weren't sure how effective it would be, and we isolated the radon gas that was trapped there and put in a different filter. And that's the thing that we were saying was surprising it was written down in our presentation, that when you first get the radon off, Pat said, well, the radon's off. And I'm like, is it though? Because there's no dose rate. And of course, from the days of Marie Curie, these things grow in, and you get those dose rates that will come. But when you don't see any dose rate readings, it was kind of hard to believe him that the magical gas had actually moved, but it certainly had. And we started to see the dose rate increase with time, as I'd already predicted with the math I'd done beforehand. But even though I'd done the math and we understood it, it was still surprising to see it. But that's our approach, is every step of the process to capture that radon rate in these relatively small filters. And I know the Belgians have done quite a bit with regards to xenon capture. And I'm sure that applies equally well to the radon capture.
Thank you. We have a question from Sabrina Banjis. She thanks you all for your presentations and asks, what would you categorize as the most important aspects to take into account for radium-226 recycling?
If I can, oh, please go ahead.
Well, just real quick, by irradiating this material at HYFER, you do produce a lot of radium-228. It is important to recycle the radium as much as possible, but the recycled radium will have higher dose rates. So when you're working with recycled radium and you're making targets, it is important to recognize that the dose rates will be higher.
Yeah, I think that specifically applies to the neutron irradiation, of course. If you use the gamma radiation, you will typically have need to recover your radium, and there the most the step which can affect you most is the transition from liquid to solid, and then eventually also from solid back to liquid once you process your targets. That is the most the step where you have the highest risk of losing part of your radium, in particular the precipitation and the reconstitution of your solid targets, if you use those. So the process that Pantera intends to use has a 99.9% recovery of the radium, which essentially means that we'll be operating with the same quantity of radium for 40 years and essentially have lost only a few grams. But that does require quite a lot of attention to the technology that you put in there.
Excellent, thank you.
I'll just add to that. When you're radiating radium in a reactor with neutrons, you will get a burnup, a few percent burnup. So yes, the radium that is brought back into the system, we have a very high recovery rate, but we're not going to recover the radium that is lost due to burnup.
Okay, next question is from Paul Girdler. What controls are used to either prevent or deal with radium-226 spills in the hot cells?
On our side, I can say that within our facility, we will have one hot cell dedicated to recovery of radium from whatever incident or other events that may occur. So we have foreseen a more multi-purpose hot cell in our facility to deal with those things. For example, if for whatever reason radium would be entering into the cooling water of the target, then that cooling water has a separate loop and could be recovered from that. Same goes for the radiochemistry processing line. So we will have a dedicated hot cell for that, next to a number of dedicated hot cells for dealing with the waste from the process itself. So we have the radiochemistry line, but there's a separate line for waste treatment, and there is a dedicated cell for radium recovery.
Dan or Joel, do you have any input for that one?
Yeah, so for at PNNL, we have secondary containment. So if there is a spill, it goes into the secondary containment, and after each batch, that secondary containment is cleaned and that material is recovered. So we're using secondary containment to minimize the impact of spills.
Yes, that's what Oak Ridge uses as well, just in case. It's also important to have a very well-trained manipulator staff, and a lack of distractions and clutter in the hot cell will reduce the likelihood of spills. But we do use a secondary containment. We also do not store material in glass or plastic for long periods of time in order to minimize the risk of failure of containers.
Excellent. Another that's kind of combination from various participants was asking more about the environmental monitoring. So including at Belgo, Thomas. So what are each of the sites doing with respect to environmental monitoring? I know you've covered some of it with the stacks and others, but I think a little bit more on tracking all of the progeny, radon and its daughters.
Yeah. For the gases emissions, we use continuous monitoring of radon in the exhaust system. We have weekly, monthly limits what we can discharge. If we see we get too close within these limits, we'll start doing some corrective measurements by doing some extra packaging to minimize the radon emission of certain drums. Most of the time, it's only one or two packages that are responsible for the high emission. We also have a series of dose rate monitoring systems around the site. And for the aqueous discharges, we have a large water treatment system, and also with continuous monitoring what we are discharging.
Do any of the other sites want to add anything else to their monitoring?
I'll just mention the way we monitor our hot cells is the hot cell air is pulled into trench filters underneath the ground, and there's radiation detectors on those, and then they go up to our mechanical room where there's duct samplers, continuous air monitors in the duct, and then that goes to a stack, one of two stacks for where we're working on this process, and there's another set of monitoring there as well, both compliance and qualitative monitoring.
Appreciate that. Thank you. There was Unfortunately, some of these questions do come in anonymously. I can't always see, but this is one about how are you tracking, measuring, quantifying the amount of radium you have at different points within your processes. So I think this goes along more with process monitoring of material.
I can jump in. Yeah, we sample, at every step of the chemical process, various cuts of from the ion exchange columns, and those are analyzed with gamma ray spectroscopy and mass scans.
Similar for our approach, and then we've also implemented some in-cell radiation field detection so that we'll be able to get a quick snapshot as well, but primarily gamma spec ICP-MS.
The Belgo process, we use the continuous radon monitoring system on all the hot cells and the different buildings to get an estimation of how much radium via the radon emanation is inside the hot cell. So if we doing decontamination works inside the hot cell, it's also useful to track the progress of your decontamination process.
And currently, we just take samples as been discussed primarily with GEA. We use a dose calibrator for quick analysis, but primarily GEA and ICP-OES to monitor our radium content.
David, did you want to add anything?
I was just going to throw in one comment. One of the challenges that our approach of doing radiation field measurement as a check is that, as we've all identified previously, timing is really critical for the ingrowth of the daughters because those are often the ones that are providing those radiation fields. So it's something that needs to be considered when you look to implement those in-process checks.
Yeah, and we use similar things. This is a little bit newer to us, and we're using a very tiny fraction of what some of these other groups are talking about, but yeah, similar types of technology.
Thank you. Question from Carl Ross, sorry. Is the carbonate the most common form of radium salt?
In our case, there have been different salts that have been produced. Carbonate is definitely among them, but there are also chlorides and other salts. It's really quite a versatile chemistry, the radium. One of the ones that's definitely to be avoided is radium oxide, because that one is a lot less soluble. Not to say not soluble.
We see sulfates as well.
Yeah, the chemistry is very similar to barium, and that's also why in the extraction of the ore at the time, barium was actually added to the process to create to put more of that chemical in, and later on often the barium was not removed. And I did see a question in the list as well, who from the purifiers, if I can abuse my access to the microphone a little bit, who from the purifiers is also extracting the barium from the radium, because that is typically left in since nobody really cared about it too much afterwards.
Our process will definitely have a consideration for removing the barium, recognizing that a lot of the early brachytherapy sources, they were actually diluted for carrier purposes when making up these small sources with barium sulfate. So the quantity needs to be confirmed, and then the process has to be responsive to those particular fractions. It comes back to each of these sources have their own history, and we need as much information to allow us to execute.
So going through our list here, from Sefer Abadi, for the roughing filters, do you use normal charcoal filters or is there a specific type of filter required?
So the roughing filters we use at Pacific Northwest National Laboratory, because we don't need to abate radon because of the limits allow us to send all of it to up through the stack. Ours are just normal roughing filters. They don't have any abatement with the charcoal.
Yeah, again, I would focus on the radon capture. You know, your roughing filters are merely just to protect your next filter, eventually your HEPA filter. So um, I yeah, very little interest in the roughing filter. They don't do a heck of a lot.
Yeah, I agree with Richard. The charcoal filters tend to maybe slow the radon down, which is more important for the short-lived radons. But for the radon 222 from radium-226, there's not much effect.
Thank you. We have, I think specifically for Joel, from Mark Garland, how does PNNL cut open the needles in your hot cell?
So we haven't. It depends on the form of the needle, the way that we cut them open, whether it's a needle or a tube or a plaque. Each of those has a different method to cut that open, and so we're using essentially multiple cutting methods in order to open them up, and it really depends upon the form.
You. The next two questions are from Jacob Baumaster. The first one is, do you observe any cracks in the glass after prolonged storage? And under what conditions, time, activity, this is specifically for you, Joel, would PNNL move to a metal vial?
So our plan is really to do a batch and quickly prepare that for shipment and ship it out. And in those cases, we would just use the glass vial. Really, the metal vial is only if you are looking at a long-term storage. Then you will need to switch to a metal vial, and we'd look at that metal vial. But our current plan is to prepare the batch and ship it out within a few days. And in that case, a glass vial is fine.
And I think the first part of that question can be open to anyone. Has anyone ever observed any cracks in the glass after prolonged storage?
The concern is more the cap and the sealing than the glass, but you will darken that glass. But we went out to 65 days. We haven't gone beyond 65 days at looking at the degradation. But there, other than darkening of the glass, we haven't seen any impact up to 65 days.
I can add a little bit. We see embrittlement. I don't think we've seen cracks in the glass vials, but we've certainly seen embrittlement. And I'm sure I'll probably get text messages from my team saying, yes, we've seen that. But it certainly darkens and gets embrittled, and then therefore you have the risk of breaking when you're trying to work with it.
Thank you. In a similar vein from Jacob, have you observed solid radium nitrate to undergo auto radiolysis with concomitant pressure buildup in a sealed container?
Maybe I can just answer. We haven't seen that, but if it's a dry, you're not going to see radiolysis, and if it's wet, you're going to see radiolysis. So it's an either or. It's really about the condition of the material.
Yeah, and if the question would be if the nitrate can actually get separated because of the radiolysis, then my answer would be no. You're not going to break that nitrate bond. But if there's water there, then effectively there's hydrogen and oxygen there. I agree with Richard.
There are reports from the 50s and 60s where they actually describe a proper drying technique, temperature and time, that eliminates the presence of residual water just for that purpose.
So Patrick, you were a little staticky. I'm not sure what's happening on your end. Well, I think we heard that there were papers from, yeah, there you go.
Yeah, from the 50s and 60s describing how to properly dry to eliminate waters of hydration.
Thank you. I'm just going through some of these other questions here. Rebecca Shaw wanted to know, can you speak to processes used in the laboratories on the instruments ICP mass spec, specifically to monitor and protect the analytical chemists during testing of radium-226 and actinium-225?
On the analytical side, of course, at SEKCN, they're used to analyzing all things from spent fuel and everything. So the radiological protection of the analytical equipment is very similar to that. It's probably a little overkill, but at least in some cases. But it's a very efficient way of using existing technology to and existing approaches to also do these measurements with the radium-226. The only thing you have to deal with in addition is the radon emission, but that's in the same way as was described before as well for us.
I'll just add two important elements to consider is one is how much mass or activity do you have? Typically for these samples, it's a lot smaller. And it's also useful to have your QC equipment set up in the same location so you can minimize the amount of air sampling or bioassay you have to do for working with radium.
We'll take this last one. I'm not sure how you all will address it, but from Diane Abu, what are the conditions in oxidizing radium? Would a long storage in water precipitate radium?
Yeah, I'm not going to take a crack at that one.
Anyone else want to try?
We store radium in low molarity nitric acid, and with time we do see a precipitate, but that radium can be recovered from that precipitate. So yeah, that's the detail I can provide on that question.
Well, we are at time. I appreciate our presenters today. Those were wonderful presentations with a lot of information, a lot of background, both what is happening at our national laboratories in the United States and industry and in Canada and Belgium. I do appreciate the flexibility with changing speakers due to unfortunate circumstances. And to our audience, thank you so much for all the questions. I apologize for the ones that we were unable to answer at this time. As a reminder, we will have these presentations on the National Isotope Development Center's website, hopefully within the next 2 weeks. And with that, I would like to close this roundtable discussion. Thank you.